All right, we are going to start with finding the domain of an equation. The domain of a function is the set of all x values. When finding the domain of a function, begin by assuming that the domain is all real numbers. So in interval notation, that was the negative infinity to infinity. Then determine if any place in the function is not defined, and exclude those values. Okay, so in other words, when we look at a function, we're going to start off by saying, hey, everything works, and then we'll look for situations where where there's some sort of violation or something where it doesn't work, and then those are the things that will kick out of the domain. Okay, so some very common examples. Rational functions have issues in that we cannot divide by 0. Okay. So to identify these bad values that do not belong to the domain, we're going to set the denominator equal to 0 and solve. And they're going to write the domain in interval notation without these excluded values. Okay. Second situation we want to keep our eye out for is an even root function. These would be like square roots, fourth roots, and anything with an even powered root. So even root functions have an issue because we cannot take the even root of a negative. So to identify these qualifying values that do not belong to the domain, we're going to set the expression under the radical, called radicand, greater than or equal to 0, and then we're going to write our domain in interval notation. Okay, so at this particular moment, we've got two scenarios that we want to consider. Well, actually, three ones. The first scenario is there's no problem whatsoever, in which case we're going to have all reals. The second case would be if we see a fraction, in which case we want to set the denominator equal to 0 and solve. And the third case is a square root, in which case we want to set the inside the radical component greater than or equal to 0 and identify what's going to make those things positive. In this first example, we can see that we've got x squared minus 7. So we start off by assuming it's everything, it's all real numbers, is in our domain, and then we look for any sort of issue, and it turns out that we're not dealing with a fraction and we're not dealing with a square root at this particular moment. So this example would be all reals for its domain. Everything can work, there's no reason to exclude any value. All right, in the second example, looking at our denominator, we see we got x squared minus 2x minus 3 equal to 0. And so what I want to know is there any x value that will make that denominator say 0? So I'm going to set it equal and solve. Okay. And we know lots of things about quadratics at this point. Hopefully you recognize that this is factorable. And it should factor into, let's see, we have 3 and a 1 there. And that negative 2 tells me the 3's got to be bigger and the 1's got to be smaller. And then I want to take each factor and set it equal to 0 and solve. And so let's see, here I would add 3 to both sides. Here I would subtract 1. And so we get that x cannot be equal to 3 and negative 1. And just so I'm consistent here, what I'm trying to say is that I don't want that to equal 0. So I'm trying to figure out what values will make it equal 0. And that would be at 3 and negative 1. So if you think about it graphically, at -1 and 3, I've got sort of open circles there, and anything else besides those two numbers are part of this domain. So then I need to figure out how to write that in interval notation. And so the domain is going to be -infinity up till -1, union -1 to 3, union 3 to infinity. And it kind of looks like the number line. So each of those three pieces, so -1 to infinity is this piece right here. Then -1 to 3 is that piece right there, and 3 to infinity. So since I broke up the number line into three components, then my interval is going to have three components in it as well. All right, next question. Here we've got another fraction, so we want to look at our denominator. So figure out where does x cubed plus 9x squared plus 8x. I don't want that equal to 0. And I can recognize that it is factorable, so I can take out an x. And that leaves me with x squared plus 9x plus 8. And I can see I can factor one more time. Let's see. I'm going to talk through this. Well, I know that's got to be x and x, because those are the only two things that give me x squared when I multiply them. And the last two positions have to multiply to 8. So it could be 8 and 1 or 4 and 2. I notice that it's got to add up to a 9, so 8 and 1 add up to 9, so it's got to be an 8 and a 1. And they all have to be positive in the factored form. So then I want to solve for x, and here I get three solutions. So I get 0, -8, -1. So that corresponds on a number line. Here's -8. Here's -1, and here is 0. So those are all open circles. So those cannot be solutions for x, but everything else will. So I want everything before it, between the -8 and the -1, between the -1 and the 0, between or past the 0. So that's what I'm going to write out for the domain. The domain will be -infinity to -8, then -8 to -1, then -1 to infinity. And I have essentially gone through, and there's four pieces. Oh, make sure I didn't miss a piece. Let's see. Oh, -1 is, oh, I missed 0. Wow, I missed the whole thing. 0 union 0 to infinity. Okay, so it's a good thing I double checked that. So here I've got 4 pieces in my number line, so I should have 4 pieces in my interval, and they should also be in numerical order, just like my number line is. Now in these three illustrations we are dealing with square roots. Actually the last case we're dealing with sort of a hybrid of fraction and square roots, but in these first two cases we have just square roots that we're trying to identify. And in a square root case, what I want to do is I want to keep the inside of the square root positive. So I wanted to figure out what's going to make 3x plus 2 remain a positive value. So I'm going to set the inside component of the square root greater than or equal to 0, and any x values that'll make that true will make the square root, will satisfy the domain requirements for the square root. So I'm going to subtract off 2, so 3x is greater than or equal to -2, and then I'll divide by 3, and so I get that x is greater than or equal to -2/3. So what that corresponds to on a number line, here I've got -2/3, and I'm going to go ahead and close that circle since the symbol says it can equal it. And as long as I'm bigger than -2/3, then we're fine. So my domain statement for this function, notice it's closed, so I'll go bracket -2/3 out to infinity. So I've got an endpoint that's got a bracket on it, it's included, and it's included in the interval notation. All right. In this next example, we have two square roots. So it's kind of like if you think of a couple of a married couple maybe that's just very picky, and one person is pickier than the other, so they both can have complaints about where they want to eat, what they want to do, but the one that's the pickiest ends up winning most of the time, right? So I was kind of thinking about it like that. We've got two square roots that are sort of battling for pickiness, and we just need to identify what's going to satisfy both of them. So we'll start with the x plus 3. So set x plus 3 greater than or equal to 0. Here we got x minus 5 greater than or equal to 0. And then I'm just going to solve those individual equations. So here I'd subtract 3, here I'd add 5, and so I get that x is greater than or equal to negative 3, x is greater than or equal to 5. And on a number line, I want to visually see this. So here we got negative 3, and everything bigger than that particular number will satisfy the first square root. Here we have 5 further on down, and everything bigger than it will satisfy the second one. So looking at the number line then, are there places where both graphs overlap? Yeah, right here. That piece right there. So starting at 5, anything bigger than it, then I can guarantee that I will have a square root that'll satisfy both components. So my domain then is going to be what I've highlighted in the picture there, that it starts at 5 and it's got to go up toward infinity. Okay, even though one of the radicals is satisfied between negative 3 and 5, it's got to be both of them to be satisfied in order to make it. In other words, they both have to be happy in order for this rule to work on them. Okay, which sort of models for us an idea of how to look at this last example, where I've got a hybrid of a square root and a fraction. So with the fraction piece, the x plus 8, I want to make sure I keep that positive. And then in the fraction case, I want to figure out what does not, what would make that x minus 3 equal 0. And then I want to solve each piece independently. So subtract off 8 there. I'm going to add 3 to both sides. And I get that x is greater than or equal to negative 8, and that x cannot equal 3. Okay, so let me put this on a number line then. So here we are at negative 8, and it's a closed circle, and it's going to shade sort of this way. Now when we get to 3, 3 is going to have an open circle on it, but we're going to keep shading that way. Okay, so as long as I'm bigger than negative 8, I skip 3 altogether. As long as I'm bigger than negative 8, then I'm fine. Okay, well, how many pieces did we break this domain up into? We broke it up into 2. So when I set up my inequality, when I set up my interval, I need to make sure I've got 2 different pieces in it. So I notice I go from negative 3 to 8. Negative 8 is included. 3 is not. And then I want the other half past 3, so 3 out to infinity. And that would be the domain for that particular function.